Okay, we are on lesson 14A and 14B, and the reason is we're fixing to begin to solve quadrilaterals and solve polynomials. And to do that, we would use the quadratic formula. Remember it? X equal the opposite of negative b plus or minus the square root of b squared minus 4ac all over 2a. So when you solve that, you're going to have to be taking square roots. And sometimes you get imaginary numbers. So we need to just remember some things before we start that. We also need to know how to simplify radicals. Now, back on page 15 of the Algebra 1 textbook, and I know we're on page 248 for this lesson, but we'll just kind of remember in our minds, square root means what? What, not half, what times itself equal? So what times itself equals 16? 4. So what times itself equals 16? 4. That's called square root. Now how do you read number 2? Cube root. And it means what number times itself 3 times will give you 64? And the answer is 4. Because 4 times 4 is 16 times the third 4 will give you 64. So what times itself equals 16? 4. What times itself 3 times equals 64? 4. Question 3 is what times itself equal 27? And there's not a perfect what times itself equal 27. Now, I'm going to give you the process out of the algebra book, but I also want to give you the real definition. The real definition, and you won't find it in my books anywhere, it really says that for a radical to be in simplest form, no factor of the radicand may be a perfect square number other than 1. Now let me explain what that just said. If we were to find the factors of 27, we would have 1 and 27, 3 times 9. So the factors of 27 are 1, 3, 9, and 27. Are any of those factors perfect squares? Well, 9 is. So to be in simplest form, no factor of the radicand other than 1 may be a perfect square. Now, if we were going to do this that way in our head, we would think, well, 27 is the same as square root 9 times square root 3. Everybody see that? And what is the square root of 9? And so we're going to get 3 square root 3. Now, that's using the official definition, okay? A radical is not in simplest form if any factor of the radicand other than 1 is a perfect square number. So we think of it as the product of that perfect square and the other factor, and we take out the square root from that. Okay, now here's the process you learned in Algebra 1, and you've learned all the way up. And that is we could use the prime factorization method. We could take 27 divided by 3 is 9 divided by 3 is 3. And then we would rewrite it as the product of those primes. Square root of 3 times 3 times 3. Now, we're going to show our work here using the prime factorization method because you need it for the harder ones. The easy ones, if you can think of it in your head, boom. Then what do for square root? You circle pairs of 2 for square root. You would circle sets of 3 for cube root, sets of 4 for fourth root, etc. Then what do? From each set, you bring 1 out from that set, and what did not get circled goes back in. Now, are you realizing here when we actually use the real definition here that 3 times 3 is really that 9? Whose square root is that 3? You see? So you see why it works. That 3 times 3 is really that perfect square factor, you see, that made it not be in simplest form according to the definition. All right, so the answer is 3 square root 3. Number 4 is asking what times itself 3 times is 625, and there's not 1. Now, it may be harder for us to do perfect cube numbers in our head. What's the greatest perfect cube factor? Well, that's not as easy, so the prime factorization method becomes really handy. So we're going to do the prime factorization of the 625. 625 divided by 5 is 125. Is that right? Divided by 5 is 25. Divided by 5 is 5. I don't know why I was second guessing myself there. So we're going to rewrite it as the product of its primes. Forget our index 3. So it's cube root of 5 times 5 times 5 times 5. Now this time my index is 3, so I'm going to circle what? Sets of 3, right? So I'm going to put my little cube root symbol back down. From the set, I bring 1 from the set out. What did not get circled in a set goes back in, and so in simplest form, it's 5 cube root 5. Okay? Any questions on that? Very good so far. Now, on page 5 of my algebra book, I taught you a little jingle. I taught you that when you multiply, you multiply the numbers and you multiply the names and you get a new name. So we need to do 21 times 14. 21 times 14 is 294. So we multiply the numbers and we multiply the names and we get a new name. The name being square root 294. But we have to make sure that our answer is written in simplest form. So we need to simplify the square root of 294. So we're going to do the prime factorization method. Divide by 2, we get 147. Divided by 3 is, will 3 go? 12, yep. How many? 49. Divided by 7 is 7. Prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, etc., right? Okay. So here's what we've got. We've got square root 2 times 3 times 7 times 7, but we've got this 42 out here, right? Now, I left some space because we may pop something out of there, right? So now what do we do? Circle sets of 2 because it's square root. So from that set of 2's, we're going to pop out, from that set of 7's, we pop out a 7, which means now outside I have a 42 times 7, and inside I have a 2 times 3, right? What did not get circled in a set goes back in. From each set you pop one out. There was already a 42 out. So now I multiply 42 times 7 and I get 294. Multiply my 2 times 3 and get 6. So in simplest form, it's 294 square roots of 6. So we multiply the numbers and we multiply the names and we get a new name. When you we don't do that exponent thing. When we get the new name, as a radical, we needed to check to see if it would simplify. So we use the prime factorization method of simplification. Any questions on number 5? Okay. Number 6. It's the same idea except it's cube root, so we're going to do our little jingle U. Multiply the numbers, 15, and you multiply the names and you get a new name. So you're going to have cube root of 48 times 100, which is cube root 4800. But we have to make sure the radical part is in simplest form. And so we're going to do the prime factorization method of simplification. So we divide by 2, we get 2400 divided by 2. Yes, sir? Okay. Divided by 2 is 1,200. Divided by 2 is 600. Divided by 2 is 300. Divided by 2 is 150. Divided by 2 is 75. Divided by 3 is 25. Divided by 5 is 5. And I'll let you catch up. So we're doing the prime factorization method of simplifying the radical. Okay? Thank you, ma'am. Okay. So we're going to have 15 cube roots of, and we're going to make us a big long cube root, and we're going to put all of those factors in there. So we already had the 15 outside. Cube roots of 2 times 2 times 2 times 2. There's 1, 2, 3, 4, 5, 6 of them. Times 2 times 2 times 3 times 5 times 5. Now the index is 3 cube root. So we circle sets of 3. We got a set of 3 2s. There's not a set of 3 of anything else, right? So from that set of 2s, we would pop out a 2. Oh, there's a second group of 3. I'm not seeing it. A second group of 3 2s. Correct. So from the first set of 3 2s, we bring out a 2. From the second set of 3 2s, we bring out a 2. And so we're going to have 15 times a 2 from the first set, a 2 from the second set, and then back under the radical goes those 3 things that weren't in the set. Okay? You understand that? 1 from each set comes out. Anything not in a set goes back in. So we're going to have 15 times 2 is 30 times 2 is 60. Cube roots of 25 times 3 is 75. And so it simplifies to 60 cube roots of 75. Any questions on number 6? So we multiplied the numbers and we multiplied the names and we got a new name. When we got our new name, it was a radical, and so we had to simplify that radical. Okay? And then we get to the part that seems to be a little more challenging for students. What we've done so far came before page 248 in the algebra book. Okay? We had learned it before that. Some of it's the first little piece. Now we're getting into those questions that I have you ask. And we get into these questions when we have a fraction situation, okay? So on page 248, it says, to see if a radical is in simplest form, you want to ask yourself these 4 questions in this order after every single step. That's very important. Question 1, will anything reduce? Question 2, will a radical break down? Now, will anything reduce is just reducing fractions with the radical names. Question 2 is, will a radical break down? That's what we just got through doing. Are there any sets? Will it break down means, are there any sets? Question 3, is there a fraction inside the square root? If there is, you split it apart. And question 4, is there a radical in the denominator? We don't allow a radical to be in the denominator. Remember that the denominator of a fraction is the name, and we want the name to be something like halves or thirds or fourths. So if we was talking about a pie, we would know how to cut it into pieces, okay? So we always make the name pure. Okay, so as we go through these next few problems, we're going to be asking ourselves those 4 questions in that order after every single step. Okay, so number 7, question 1, will anything reduce? Yes, we can reduce this radical with radical. What is square root 75 divided square root 3? Square root 25. Question 1, will anything reduce? Well, there's not any fractions. You don't reduce if it's not a fraction. Question 2, will that radical break down? Yes. What times itself is 25? 5. Well, we know we're done because it's a whole number. Okay? Now what people will start doing is you will start trying to do whatever it looks like can be done rather than asking yourself those 4 questions in that order after every single step. And you will create something that's more complicated if you don't watch out because you didn't do it in that order. Okay? Number 8, question 1, will anything reduce? No, because it wouldn't reduce anyway, but you can't reduce numbers and radicals even if they look like they would reduce. Question 2, will a radical break down? That means if you took the 3 and did the prime factorization, would you get a pair or a set? Of course not. Question 3, is there a fraction inside the square root symbol like that? No. If there was, here's how you would fix it. You would just split it apart. But then it would have problem number 4. If there was a fraction, you just bust it apart. Okay? Now, question 4, is there a radical in the denominator? Yes. Now, this is important. Some of you have dealt with easy ones so long that you don't really know how to do it. You don't know the rule. You just do something because it works on the easy ones. So a lot of you say, well, I'm just going to multiply by square root 3. Well, you're going to, and it's going to work, but do you know why you multiply by the square root of 3? It actually says, are y'all looking at page 249, I believe? Let me make sure you're in the right page. In the middle of the page, fixing problem 4. Do y'all see that? This is very important that you learn it this way. You're going to multiply by the square root or cube root of blah times blah times blah, so that each factor involved appears the index number times. In other words, I need a situation where I've got a pair of 3's that I can pop out so that there's nothing left under the radical. I need there to be all sets. Well, if I'm going to have a set of 2 3's, then what do I need to multiply by? 1 more 3, 2 more 3's? What do I need to multiply by? Well, 1 more 3, because if I multiplied by 1 more 3 with the one I've already got, that would give me a set of 2, which would pop a 3 out of the radical with nothing to go back in, you see. So it's not you're going to multiply it by itself. You're going to create a set of primes so that from the set you pop it out. The idea of creating sets is what we're after, okay? Now, whatever you do to the denominator, you have to do to the numerator. So in the numerator, we're going to have 11 times the square root of 3. So we get there, 11 square root 3 over 3. Now we go back to question 1. Will anything reduce? Nope. Will a radical break down? Will the square root of 3 break down? Nope. Is there a fraction inside the square root? Nope. Is there a radical on the bottom? Nope. We got a no to all 4 questions. Nope, 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 nope. So we know it's in simplest form. Any questions on that? We call this, see, a square root is an irrational number. 3 is a rational number. So we say that we rationalized the denominator. We took it from being an irrational number to being a rational number, okay? All right? They're going to get a little harder as we go, so we hope you're getting the process down. Number 9. Number 9, question 1, will anything reduce? Well, when we reduce number with number and radical with radical. So we think about the 48 and the 36, and we think about the square root 35 and square root 30. What's the greatest common factor between 48 and 36? 12. So we're going to divide both of those by 12, and we're going to get a 4 and a 3. Now, on the radical part, what's the biggest radical that will divide into both? Radical 5, square root 5. Square root 5 will go into square root 35 and square root 30. We're dividing by the greatest radical factor, you see. And on top, square root 35 divides square root 5 is square root 7. And on bottom, square root 30 divides square root 5 is square root 6. And so this reduces to 4 square root 7 over 3 square root 6. We reduce radical with radical and number with number. Okay? We said we got to there. Now, we go back to question 1. Will anything reduce? No. Question 2, will a radical break down? Well, let's see. If we took that 6 divided by 2 is 3, did you get any sets? Any sets of primes? Nope. So will it break down? No, because there's no sets to pull one out, you see. It will not break down. Question 3, is there a fraction inside of one of those radicals? No. Question 4, is there a radical in the denominator? Yes. Now, y'all listen to this. This is important. We're going to rationalize the denominator. We need to get rid of that radical. To do that, we multiply by the square root of blah times blah times blah, so that each prime involved in that, there they are, 2's and 3's, appears the index number times. Now, what's the index on square root? It's an understood 2. So each prime involved in that 6 needs to appear twice. How many times has the 2 already appeared? So how many more of those do we need to have 2? 1 more 2. How many times has the 3 appeared so far? Only 1. So how many more do we need? 1. So we're going to multiply by the square root of 2 times 3 so that we have a pair of 2's and a pair of 3's. Now here's what we really have, just so you can see. From the square root of 6, we've got this, correct? And now we've just added this. And so now we have a pair of 2's and a pair of 3's. And so we're going to pop out a 2 and pop out a 3, which is like popping out a 6. We rationalize the denominator, whoops, times 3, right? We already had this 3 times, we popped out a 6. Square root of 6 times square root 2 times square root 3 is plain old 6. We created a set of 2's and a set of 3's. Do I need to do that again for anyone? Yep. Okay, let's do it one more time, because I want to show you what the rule says. Let's back up to here. Okay. When we took that 6, we said, will the 6 break down? Well, it's a 2 and a 3, so there's no sets. So it wouldn't break down, but now we want to rationalize the denominator, get that square root off. If we were going to get the square root off, there would need to be, everything would need to be in a set, right? Inside the radical. So that that pops out and that pops out and there's nothing to put back in. So we're trying to create sets. Sets of what? Well, the understood index is 2. So we need sets of 2 of each prime involved. So we need to multiply so that we have 2 2's. Well, I've already got 1 right here, so I need 1 more, which would really create a pair of 2 2's, so a 2 could pop out. And I've only got 1 3, so I'm going to multiply by another 3, which would really create a pair of 3's, and a 3 would pop out. Okay? So I already had the 3 out there, so it's got to go back out. But what I've done is I've created from those things a pair of 2's and a pair of 3's. So I pop out a 2 and pop out a 3, which means together I pop out a 2 times 3 or a 6. Okay? Whatever you do to the denominator to rationalize it, make the radical fall off. See, that radical's not on the 6 anymore. We have to do to the numerator to make equivalent fractions. And so on the top, I'm going to have that 4 that was already out there. And then I'm going to have square roots of 2 times 3 is 6 times 7 is 42. So that's what I've got. And we know that 3 times 6 is 18, which we could have already done, right? So I'm going to go ahead and change that to an 18. You might need to see that step. Maybe you want to write another step so you don't lose it. That's fine too. Now back to question 1. Will anything reduce? Yes. 2 will go into 4 2 times. 2 will go into 18 9 times. So now we have this. So back to question 1. Will anything reduce? No. Will a radical break down? Well, we better check out that 42, right? 42 divided by 2 is 21. Divided by 3 is 7. Are there any sets of primes? Nope. There's no sets of primes. A single 2, single 3, single 7. So the radical will not break down. Is there a fraction inside that radical? Nope. Is there a radical in the denominator? Nope. So we got a no to all 4 questions. So it must be in simplest form. Any questions on that? Everybody good so far? Okay. Number 10. Want to at least get this one done. Number 10, question 1, will anything reduce? No. Will a radical break down? Well, we may not be sure about that 300, right? So we're going to take 300 divided by 2 is 150, divided by 2 is 75, divided by 3 is 25, divided by 5 is 5. Now, we need sets of what? We need sets of 3. So will the radical break down? No, because there's no sets of 3. Okay? So question 1, will anything reduce? Nope. Question 2, will the radical break down? Nope. Question 3, is there a fraction inside either radical? Nope. Question 4, is there a radical in the denominator? Yep. So we're going to multiply by the cube root of whatever it takes so that each prime involved in the 300 appears how many times a piece? 3 times a piece because it's cube root. Now how many times has the 2 already appeared? So what do we need? 1 more 2. That would give us a set of 3. Okay? How many times has the 3 already appeared? Once. So we need how many more? 2. How many times has the 5 already appeared? Twice. So we need how many more? 1. To rationalize the denominator, we multiply by the square root or cube root of blah times blah times blah times blah, such that each prime involved will appear the index number of times. Okay? And whatever you do to the denominator to rationalize it, you must also do to the numerator so that the result is an equivalent fraction to what you started with. Now, on the bottom, we already had that 7 out there. I'm going to use my colors. We've got 1, 2, 3 2's, so out pops a 2. We've got 1, 2, 3 3's, so out pops a 3. We've got 1, 2, 3 5's, so out pops a 5. You see what we're doing? We're creating sets of primes so that everything pops out. Okay? We call it rationalizing the denominator. Rationalizing the denominator. Okay? All right? You see what we're doing? Now, on the top, we already had this 6 outside. This is going to be out there. Cube roots of. Now, notice when you look at that, there's 1 11, 1 2, 2 3's, and 1 5. Is there a set of 3 of any of those up there? So it's not going to break down. Nothing can pop out. So we're going to multiply all that stuff. So we'd get, I'd probably go 3 times 3 is 9, times 11 is 99, times 10 is 990. That'd probably be the easiest way to go at it. Okay? So we have 6 cube roots. Is it okay if I just cancel that out right there? Would that be all right with y'all? If I cancel that 6 with that 2 and 3? And I'm going to have, so I'm going to have the cube root of 990 over 5 times 7 is 35, right? Or you can do that in 2 or 3 steps if you want. Kind of wonder why I multiply them and then reduce it, and you just knock it out of there. Question 1, will anything reduce? Nope. You can't reduce a radical in a number. Will the radical break down? Well, we know where it came from. A single 11. We're looking for sets of 3. A single 2. A pair of 3s, but we need a set of 3. And a single 5. Well, it's not going to break down because it'd go right back into those numbers we just multiplied together. Is there a fraction inside the radical? Nope. Radical in the denominator? Nope. So that's it in simplest form. Any questions on the first 10? All right, we're going to stop there, and we're going to do number 11 next recording, and we'll do the imaginary numbers with it, okay? Appreciate your attention.